the RSNA, this is the Radiology Artificial Intelligence Podcast. My name is Paul Gee, and I'm a radiologist at the University of Maryland and co-host of the podcast.
And my name is Tejani, and I'm a radiology resident at the University of Texas Southwestern Medical Center and co-host of the podcast. Each month, we dive into the hottest topics in radiology AI and talk with leading experts, thought leaders, and movers and shakers in the field.
Welcome back to another episode of the Radiology AI Podcast. On this episode, we continue our conversation with Drs. Trivedi and MinJae Wu about the EmBED dataset. Last time, you heard all about our guests' experiences organizing the dataset. Now, find out more about best practice recommendations when using this dataset and how datasets like EmBED can encourage the creation of generalizable models for breast imaging.
Hari M. Trivedi, MD, is an assistant professor in the Department of Radiology and Imaging Sciences, with a joint appointment in the Department of Biomedical Informatics at Emory University School of Medicine. Dr. Trivedi is the co-director of the Health Innovation and Translational Informatics, also known as HITI Lab, at Emory University, where he works on multiple machine learning projects related to radiology and development of large datasets. His clinical expertise is in emergency and trauma imaging with fellowship training in musculoskeletal imaging. Dr. MinJae Wu is currently an assistant professor of data science in the School of Data Science and Analytics at Kennesaw State University in Georgia. His research interests lie in the area of healthcare data science, with a focus on his applications in medical imaging, clinical text, and clinically oriented speech. He spent the early years of his career developing a variety of clinical decision support tools to assist combat medics on the battlefield. His ongoing projects aim to develop various early cancer screening platforms that are fair and explainable for the detection of breast cancer, oral cancer, lung cancer, and hepatic metastases. So I wonder, can you recommend some best practices for use of the dataset? I know you had mentioned some challenges with maybe identifying cohorts that, maybe there's some unforeseen pitfalls. I'm going to guess that no one has more experience than you two, so I'm curious if you have some advice for anyone who might be wanting to kick around the tires.
I'll only say one thing, and then I'll let MinJae talk. I'll say read the README, because 90% of the questions we get are answered in the README. And I get it, and it's long, but with a data set that's this robust, the clinical data has over 200 features, and each feature has hundreds of potential values. The metadata is full DICOM metadata, so you've got literally hundreds of features. And then we've run what we call, like I mentioned earlier, helper models to abstract additional data from either the metadata or the pixel data, right? And so there's additional features in there that we've handcrafted and add back to the core data set. We also provided a sample notebook. So step one is for everybody to go to GitHub, read the README backwards and forwards, and use the sample notebook. But beyond that, I think MinJae's students have really, probably beyond myself, MinJae and his students have used the data set more than anybody else and dug into it. And I think he could speak really well to the best practices there.
Yes, I think I can point out something in general. So, like I said, the dataset contains a lot of clinical details, and based on my own experience, I would highly encourage anyone to have clinicians as part of their team. So while some things in the dataset may seem very obvious, there may be some clinical complexity that are not easy to be spotted and easy to be overlooked. So these additional details open up the new opportunity, but at the same time, it challenges user set. So with that, I think that they should have someone with a significant clinical background on their team, because the process may require some careful consideration of clinical context.
Something that Hari said caught my mind, and this is something I think about when I see data sets, and I feel like I've been trying to be more cognizant prospectively, but let's talk about cybersecurity. Not really cybersecurity, more patient privacy. So how do we ensure that all patients in this data set remain anonymized, with DICOM metadata there? We've seen papers where there are if you will, hidden features or more salient or less salient features that maybe models pick up on that we can't with our human eye. But in the process of creating this data set, what are your thoughts on maintaining patient privacy, and were there any steps put into place to ensure long-term protection?
That was something that we paid a lot of attention to. I think it goes without saying that when you're releasing a data set of this scale, patient privacy is extremely important. Patients entrust us with this, with their healthcare data, and the last thing we want is a breach. And in fact, I think the time between when we got greenlit to release the data set from the IRB and School of Medicine to when we actually released it was about 6 months. And that's after we had already de-identified the data for internal use. But we applied an entire different set of standards to do this public release. With a data set of this scale, it's not feasible to check every single image. So we had to come up with, creative ways or tried and tested ways to identify any PHI in these images. Some of the good news is that mammograms typically don't have any PHI on them. They'll have a marker that says left or right breast and then the initials of the technologist. That initial of the technologist could potentially be traced back to an institution, but there's no secret that this is the Emory breast imaging data set. So us keeping technologist initials in there doesn't matter. They can't be linked back to an individual patient. We did remove things like the ordering provider and the interpreting provider, even though technically, again, those are not PHI, but those are coded in the data set with randomized values. So you can see radiologist 1 interpreted these exams, radiologist 2 interpreted these exams. We ran the data through our own custom de-identification pipeline, which looks at over 200 DICOM metadata tags, decides which ones to de-identify, which ones to remove outright, and which ones to leave alone. So as you can imagine, the things that we removed outright were patient name, addresses, social security, dates of birth, that kind of thing. The 3 things we de-identified were patient ID, accession number, and study date. Study dates are shifted such that they're the same within a patient, but different across patients. So you maintain the temporality between exams for a given patient. You don't distort, the time between exam 1 and exam 2. But every patient has a unique date shift. The patient IDs are de-identified and the accession numbers are de-identified. So you have identifiers for them, but they're not linked back to the original data set. And then for pixel data, we used 2 different commercial grade tools for pixel de-identification. It turns out that some screen save images or secondary captures did contain things like dates and timestamps. So rather than, and those were not really needed as part of the public release, we use them as part of the data curation process to find regions of interest, for example. But once we'd extracted those, we didn't need those anymore. So an extra measure of safety, we removed all secondary capture objects. So what you're left with in the data set is just de-identified DICOM files for 2D CView and tomosynthesis, and de-identified DICOM metadata. And then the tabular data that's in the clinical table is essentially de-identified by nature. It's all coded. There's a legend that tells you what's what. And it has similar columns, patient ID, an accession number, and a date, which are de-identified the same way. We did take care for zip codes as well. There's about 20 zip codes in the United States that have less than 1,000 people. If you have those zip codes in your data set, you have to truncate the last 2 digits. But since none of those zip codes were present in Georgia, we didn't, or I guess in our patient population, we didn't have to worry about that. So, it's funny because I had all these processes in place, and I think for the last month or month and a half, I think every night I, just wrung my hands and tried to think of any other rocks to look under. And eventually I got to a point where I said, okay, well, we don't know what else to check and we don't know where else to look. And we've done everything really, I think, to a world-class standard, as far as I know, to de-identify this data. And we feel pretty confident that, that it's safe. And on top of that, one of the reasons that we release the data but have people request permission to access it is that so we can track who's downloading it. They're not permitted to share it with somebody else. So in case we have an issue down the road, unforeseen, we know exactly who has copies of the data set, and we can reach out to them and ask them to purge their existing copy and download a new copy.
I completely agree, and just wanted to say thank you for being so thoughtful and for sharing those details, because I think it does set a precedent for future data sets, we're going to start seeing more, and hopefully future groups can be as thorough as you and your team were in this process. So when we think about other data sets and some of the challenges that they've had, you think about selection bias and limited generalizability that can limit the use of those data sets outside that institution or outside a specific clinical context. But it seems like this data set, especially with its more diverse demographic set, can address some of those issues. But can models that are built or trained on imaging data from this data set be completely generalizable in terms of race or geographic distribution? Things like modality, not really modality, but vendor equipment, specific settings along those lines. Are there any limitations that developers should be aware of before using the data set?
I think absolutely. There's always limitations with any data set release, even if you pull from 10 institutions with 1 million patients. There are grades of generalizability. I don't know that there is a such thing as absolute generalizability. Anybody's using, and so we're at Emory implementing our first commercial AI model next week. And one of the things that we requested is that we pull 5,000 cases and evaluate the model performance on our data. This set of models has been deployed at 50 institutions in the past. I think it's everybody's responsibility to ensure models work well on their patients. I do believe that this data set is more generalizable than other data sets in our domain and than most medical imaging data sets because we do provide demographics information and it is diverse. But I think it would be short-sighted to say that it's fully generalizable and any model trained using this data will work anywhere and everywhere. We do have a pretty strong skew towards one vendor, right? And that vendor is the dominant vendor for mammography in the United States, but a lot of places don't use them or don't use them exclusively. And we have 95% of our images from that one vendor. Even beyond that, if you have the same scanner, the same mammography machine at two sites running the same piece of software, the images can still be different subtly because that site chooses what they want their post-processing curves, window leveling, brightness, contrast, sharpening to look like. And so same device, two institutions can spit out different images depending on the preferences of that institution. Human beings can see through most of that stuff. I think it's clear based on the body of knowledge we have now that machines don't do a good job. They will continue to get better. I would love to see models created using this data set or created using other data sets and validated, vice versa, because I think that's the real ticket. And unfortunately, right now, some of the largest public mammography data sets that have this type of granular data are analog, right? They're from old film mammograms, or they're not, or they may be digital mammograms, but they're lacking the granularity of what we have. So it's hard to perfectly test.
I'd just like to add what just Hari mentioned. So when we got access to dataset, one of the very first things that we tried was whether the existing state-of-the-art model is generalizable to Emory dataset. And we found out that the biggest barrier in this field of breast cancer imaging is the old dataset. So those publicly available datasets are old, and whatever model they implemented or guided by those dataset may not be uh, applicable in contemporary clinical settings. So we found out some of the models guided by those analog images are not really performing well. And we also tried some experiment mixing up the old dataset with the new dataset from Emory and found out it actually interferes model performance. So those models trained a mix of old dataset and the new dataset, or exclusively on old dataset, uh, do not perform reasonably in over digital mammograms.
Yeah, I think that's really interesting. When I hear Hari and MinJae, you guys talk about some of the considerations and things that you've learned about building this data set. To me, one of the clear messages is we really need to have collaboration between MDs and PhDs. And moreover, domain experts, even within a given field of radiology, let's say breast imaging. And this is actually a recurring theme on the podcast, is this multidisciplinary collaboration. I think the journal, Radiology AI, is pretty unique. Our editorial board has a mix of people across the spectrum, from super technical to super clinical. So I'm wondering, maybe stepping away from the data set per se, can you talk to us more about your own experience working with a team of radiologists and engineers? Did you have any things that you weren't expecting, maybe good or bad? And furthermore, do you have any advice for readers working on similar types of initiatives?
Yes, so based on my own experience, it's continuous learning process that those clinical informations or knowledge is not just required by clinicians, but also required by engineers. And clinicians, they should know some engineering knowledge as well to see if the models within the clinical context or not. So this has I've been enjoying this learning process. I whenever we do the weekly memo meeting, I learn new things. And with the experiment setting, I sometimes there's some clinical issues that none of our engineers could think of, and Harry oftentimes point this out and explain to us. That costs a lot of time. It's time consuming. I'm learning, but with that, I we can ensure that whatever we are working, whatever model that we are trying to develop, or whatever strategy that we are trying to suggest, is strictly within clinical context and has an actual impact on those patients out there.
I completely agree with MinJae. I think a couple things that I would add are domain expertise just extends beyond a physician or a radiologist. Uh, we're in this era of AI model development that really requires subspecialty expertise, right? We're beyond the intracranial hemorrhage and lung nodules. We're kind of diving deep into prostate, PIRADS, LIRADS. Every single one of my projects, every single one of my grants, industry collaborations, data sets, whatever it might be, we have a domain expert besides me from that subspecialty. So we have breast radiologists that we consult with. We're working on a prostate MRI data set. We've got body radiologists working on a knee radiograph data set. I'm trained musculoskeletal imaging, but we have two orthopedic surgeons helping with that data set because every data set you build doesn't exist in a vacuum of just imaging. The true value of the data is unlocked when you tie it to clinical data. And that clinical data, that clinical expertise comes from the people that deal with this data day in and day out. So for prostate, you have to understand the management of a Gleason 6 and a Gleason 7 lesion, not from the body radiologist, but from the urologist, right? And and for breast, we talk to the breast radiologist, the breast pathologist, the surgical oncologist. So I think it's very, very important because I've seen it happen time and time again that you operate in your own bubble for 6 months, 12 months without asking the right questions. And you realize that you've got a really awesome model with an awesome AUC that nobody cares about and nobody can use because you answered the wrong question, right? And it could have just been some simple little thing that you looked over or glossed over. I think one other thing that's really interesting is when we force ourselves to craft these models, you force yourself to separate data into classes, positive, negative, or maybe multi-class models. And MinJae and I have been going back and forth on this quite a bit with this model we're trying to develop for abnormality detection in mammography of what classifies as an abnormality. Is it just a BI-RADS 1 or 2 on screening? But what if it's a BI-RADS 0 that became a BI-RADS 1 or 2 on diagnostic? Is that a normal or abnormal exam, right? And going through this because you have to ultimately provide a model to train and test with a set of, you have to draw a hard line between class A, B, C, D. And it really forces you to think about the problem in a way that you don't think about in your regular clinical practice, right? Another example is if you're looking at intracranial hemorrhage, we may say that there's a subdural or subarachnoid or intraparenchymal. And sometimes you can't tell if it's a subarachnoid or intraparenchymal, right? If it's close and it's right there on the edge. It forces you to think about those nuances and those edge cases and all of these little things because that will significantly affect the way the model is trained. And if you go and try to get that model through FDA clearance, you have to make a claim as to what this model does and what it predicts and what it diagnoses. And you can't do that if you haven't gone through all these steps of really thinking hard. So it's in that way, it's been a really enjoyable experience and set of conversations anytime we do this, because we have to go back and things that we take for granted or do by nature as radiologists interpreting without thinking exactly about what classes we're defining. Now you have to define those classes.
And speaking of classes, a lot of publicly open data set out there are defined using pathology information. But people are training those models with the images, and what image has is the radiographic information. So sometimes there can be a mismatch happening between the pathology information and the radiographic information, which is not well known by many people.
No, I completely agree. I just want to say thank you for that rich advice. I think especially when we think about breast imaging and biorads, it's so hard to assume the nuances unless you actually worked in the field. And then to translate that in the technical side is an equally difficult task. So I think that point is especially salient here. As we wrap up, and I say that with some sadness because I've really enjoyed this conversation, but as we wrap up, what can our listeners expect in terms of updates and where to access them? I know we talked about where they can get the current data sets. Is that the same process for any future iterations?
Yes, we expect to continue to update this data set hopefully every 6 months. So we have some things in process right now, which I think are kind of exciting. We have identified almost double the number of exams as we originally had. So this data set will be increasing in size by 2.5 fold pretty shortly. That's number one. Number two is we've identified the MRI and ultrasound exams, which we didn't really touch on earlier. That's going to be a challenging set of data to work with, only in regards to annotations. We'll still have the entire ultrasound exam, the entire MRI exam, the imaging descriptors in tabular format, the pathologic outcomes in tabular format. But what will be difficult, I think, with MRI and ultrasound is pixel level annotations, right? We hope that if we release these, some groups will come up with creative methods or put in some elbow grease and do annotations and then release those back to the community. So those are the two things that I think I'm most excited about. And then thirdly is I'm hoping sometime this spring or summer we can actually unlock our digital breast tomosynthesis files. I've got a lot of people interested in working on 3D mammography, and I think it's really, AI is a great application for 3D because 3D is significantly more sensitive and specific, but it just takes too long to read right now, which is why a lot of radiologists may not prefer it. It does take longer to read than a typical 2D mammogram. But if we can use AI to guide radiologists to even the correct slice or suspected lesions, I think it would save a lot of time. So that's what we hope. The data set will just be versioned on the same AWS Open Data program. So if you have an old version of the metadata, your files will be intact and you can continue to access that, and we'll just continue to add files to the repo or to the bucket and make new versions of the metadata and clinical data. So we're hoping that it's a non-destructive process, that whatever version you're working with will continue to function fine. And when and if you decide to upgrade, the new version will contain everything V1 contained plus more.
Also, we are expanding resources for supporting model development. So if you go to AWS website, there's a GitHub link to the page. And if you go there, you'll see a lot of example notebooks for how to utilize dataset. And also every study we publish out of this data set has some kind of publicly available course that we use to perform experiment. And that will also grow up over time, and those will be valuable resources that can save time for those users.
All right, so Hari, MinJae, thanks so much for joining us here on the Radiology Artificial Intelligence podcast. It's been a pleasure talking to you about everything from how to create a data set to the trials and tribulations to how we can really future-proof these for the impending AI revolution. So thanks so much again. I really appreciate it, and I'm sure our listeners have enjoyed this time as well.
Great. Thanks so much.
Thank you.
Thanks for joining us for this episode. We hope you enjoyed the conversation.
Thanks to all our panelists involved in the conversation and for sharing their expert insight. We hope that you've enjoyed this episode of the Radiology Artificial Intelligence Podcast. Shout out to Uriah Shemchisen for our podcast music and to the RSNA podcast staff.
Email us at podcasts@rsna.org anytime with questions, feedback, or suggestions.